Right now, you're standing upright. You feel like you're pointing toward the sky, toward up. But someone standing on the exact opposite side of the planet is also upright, and they're pointing in the completely opposite direction. So, which one of you is actually pointing up? Here's the unsettling answer. Both of you are right, and neither of you is right. Because up, as a universal direction, doesn't actually exist. It never has. You can launch a spacecraft above every planet in the solar system, above the sun itself, above the entire disk of the Milky Way, and you still won't be traveling up. There is no cosmic ceiling, no universal top, no direction that everything in existence agrees is upward. And by the end of tonight, you're going to understand exactly why. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've done every single day of your life without thinking about it. Standing up. Right now, wherever you are, gravity is pulling you downward. Your feet press into a surface. Your body knows which way is down because every bone, every muscle, every fluid-filled chamber in your inner ear is telling you the same thing. Down is beneath your feet. Up is above your head. This feels so obvious, so absolute, so permanent that it barely seems worth mentioning. Of course, down is down. Of course, up is up. These aren't things you question. They're things you feel with your entire body from the moment you're born. Babies learn it before they learn language. Long before a child knows the word gravity, that child knows which way things fall. Drop a toy and it goes down. Throw a ball and it comes down. Jump and you come back down. Down is one of the first facts of existence. It never changes. It never takes a day off. It is always there, pulling everything toward the ground, every second of every day of your entire life. Because of this, our brains treat up and down as fundamental features of reality. They feel like they're built into the structure of the universe, as real and permanent as space itself. North, south, east, and west might need a compass, but up and down need nothing. You just feel them. They seem to exist on their own, independent of any tool or decision. This sensation is so deeply wired into us that it shapes how we think about everything. We build houses with floors at the bottom and roofs at the top. We stack things. We hang things. We talk about climbing up in life and falling down in failure. Our entire language is organized around a vertical axis that we assume is universal. Heaven is up. Underground is down. Progress is upward. Collapse is downward. We map our emotions onto it, our status, our architecture, our mythology. The vertical axis isn't just a physical direction to us. It's a metaphor for almost everything. And here's the thing. On the surface of Earth, this intuition works perfectly. It never lets you down, if you will excuse the expression. Gravity is remarkably consistent at the surface. It doesn't change direction. It doesn't flicker on and off. It doesn't have moods. Wherever you stand on Earth, gravity pulls you toward the ground at an acceleration of roughly 9.8 meters per second squared. That number barely changes whether you're at the equator or at the poles, whether you're at sea level or on top of a mountain. The variation is tiny, less than 1% across the entire surface of the planet. For all practical purposes, gravity on Earth is constant and uniform. It always pulls straight down, and straight down is always the same direction relative to the ground beneath your feet. So your brain never has any reason to question it. Why would it? The signal never contradicts itself. Down is always down, up is always up. End of story. But here's where the story actually begins. Because down is not pointing towards some universal flaw beneath the Earth. Down is pointing toward the center of the Earth. And that distinction changes everything. Think about what gravity actually does. Every object that has mass pulls on every other object that has mass. This is one of the most fundamental discoveries in the history of science, described by Isaac Newton in the late 1600s. The more massive an object is, the stronger its gravitational pull. The closer you are to it, the stronger the pull. Earth is extremely massive, about 6 trillion kilograms, and you are standing right on its surface, as close to all that mass as you can get. So the pull is strong, it accelerates you toward Earth's center at 9.8 meters per second squared. That acceleration is what you experience as weight. It's what makes your feet press into the floor. It's what makes dropped objects fall. And it always points in the same direction, toward the center of the Earth, not toward some absolute bottom of the universe, toward the center of this particular ball of rock and iron that you happen to be standing on. But here's where it goes even deeper. Because Newton's picture of gravity, the one where mass pulls on mass across space, is not the full story. In 1915, Albert Einstein published a theory called general relativity that completely reimagined what gravity is. In Einstein's picture, gravity is not a force at all. It's not something reaching out across space and pulling on you. Instead, gravity is the curvature of space-time itself. Massive objects like the Earth don't pull things toward them. They warp the fabric of space and time around them, and other objects follow paths through that warped geometry. Think of it this way. Imagine stretching a sheet of rubber tightly and placing a heavy bowling ball in the center. The bowling ball causes the rubber to sag, creating a curved depression around it. If you roll a marble across the sheet, the marble doesn't travel in a straight line. It curves toward the bowling ball, not because the bowling ball is reaching out and pulling it, but because the surface itself is curved. The marble is just following the shape of the sheet. That's a rough analogy for what Einstein described. Earth curves the space-time around it, and everything nearby, including you, follows paths through that curved space-time. Now, here's the part that changes how you think about down. In Einstein's framework, an object in free fall is not being acted on by any force. A skydiver who has just jumped out of a plane before the parachute opens is not being pulled downward by gravity. That skydiver is following the most natural, straightest possible path through curved space-time. Physicists call this path a geodesic. It's the equivalent of a straight line in curved geometry. The skydiver feels weightless during the fall, not because gravity has stopped, but because free fall is the natural state of motion in curved space-time. There is no force being applied. There is nothing pushing or pulling. The skydiver is just moving along the shape of the universe. So what creates the sensation of down? What creates the feeling of weight, the pressure on your feet, the tug that tells your inner ear which way the floor is? It's not gravity pulling you down, it's the floor pushing you up. When you stand on the ground, the solid surface of the Earth is preventing you from following your natural geodesic path, which would be to fall freely toward the center of the planet. The ground is pushing you away from that natural path, accelerating you upward at 9.8 meters per second squared. And your body interprets that push, that acceleration away from free fall, as the sensation of weight. The sensation of down. This is a complete inversion of how we normally think about it. You feel heavy not because something is pulling you down, but because something is pushing you up. The floor is the active player. Gravity in Einstein's picture is just the shape of the space you're in. Down is not a direction imposed on you by a force. It's a sensation created by a surface that refuses to let you follow the natural curvature of spacetime. Remove the surface, let yourself fall freely, and the sensation vanishes. You feel weightless. You feel no down. Not because gravity is gone, the spacetime is still curved, but because nothing is pushing you away from your natural path anymore. This is exactly what happens to the astronauts on the International Space Station. They are in curved space-time. They are following geodesics. The Earth's mass is still warping the space around them, but no floor is pushing against them. No surface is preventing their free fall, and so they feel no direction. No down, no up, nothing. The vertical axis dissolves completely, not because they've escaped gravity, but because they have escaped the push of a surface. This means that down is even more local and more contingent than Newton's picture suggests. It isn't just that down points toward the center of the nearest massive object. It's that down only exists at all when you're in contact with a surface that resists your free fall. Take away the surface and the direction itself vanishes. Down is not a property of space. It's not a property of gravity. It's a property of your interaction with a solid surface in curved spacetime. No surface, no down, no down, no up. The vertical axis isn't just local to a planet. It's local to the experience of standing on something. This means something profound. Imagine two people standing on opposite sides of the Earth. One person is standing in Quito, Ecuador, near the equator. The other person is standing in Singapore, roughly on the other side of the planet. Both of them feel perfectly upright. Both of them feel gravity pulling them downward. Both of them would tell you with complete confidence that they know which way is up. But if you could somehow see both of them at the same time from a point in space, you would notice something remarkable. They are pointing in almost exactly opposite directions. The person in Quito feels up as the direction away from their feet, pointing out into the sky above South America. The person in Singapore feels up as the direction away from their feet, pointing out into the sky above Southeast Asia. Those two directions are roughly 180 degrees apart. They are as different as two directions can possibly be. So, who is right? Which one is pointing toward the real up? The answer is both of them and neither of them. Both are correct in their local reference frame. Gravity is pulling each of them toward the center of the Earth, and up for each of them is simply the opposite of that pull, the direction away from Earth's center. But those two ups point in completely different directions because the two people are standing on different parts of a sphere. There is no tiebreaker. There is no cosmic judge who can look at both of them and say, actually, the person in Ecuador is pointing toward the real up. The universe doesn't work that way. There is no universal up for the judge to compare against. There is only local up, which means away from the nearest massive object. And that direction depends entirely on where you happen to be. This isn't just a thought experiment. It has real, measurable consequences. The engineers who build skyscrapers in different cities around the world know this. A skyscraper in New York and a skyscraper in Sydney both point up. But those two ups aim in very different directions because the cities are on nearly opposite sides of the planet. Every plumb line on Earth, every level, every tool that measures the vertical points toward the center of the Earth. Not toward some fixed point in the sky, not toward some absolute ceiling, just toward the center of the local mass beneath it. Now let's leave the surface and see what happens to up when you go higher. You might think that as you travel away from the Earth, up will become clearer. After all, you're leaving the confusing surface of a sphere behind. You're heading out into open space. Surely, once you're far enough away, up will assert itself. But the opposite happens. The farther you get from Earth, the weaker and more arbitrary up becomes. Consider the astronauts aboard the International Space Station. The station orbits Earth at an altitude of roughly 400 kilometers. At that height, Earth's gravity has not gone away. This is one of the biggest misconceptions about space. People see astronauts floating inside the station and assume gravity has stopped working. It hasn't. At the altitude of the station, gravitational acceleration is still about 8.7 meters per second squared. That's roughly 89% of what you feel on Earth's surface. Gravity is very much still there. The reason astronauts float is not because gravity has disappeared. It's because the station and everything inside it is in free fall. The station is falling toward Earth every single second. But it's also moving sideways so fast, about 28,000 kilometers per hour, that as it falls, the Earth curves away beneath it. The station keeps falling and keeps missing the ground. That is what an orbit is. It is a continuous state of falling without ever hitting anything. And because the station, the walls, the equipment, and the astronauts inside it are all falling together at exactly the same rate, nobody inside feels any pull. There's nothing pushing them against a floor. There's nothing telling their inner ear which way is down. From the perspective of someone inside the station, there is no down. There is no up. There is just floating. This is what physicists call weightlessness, and the name is slightly misleading. The astronauts still have weight in the sense that gravity is still pulling on them. They would weigh almost the same on a scale at that altitude if the scale weren't also falling. What they've lost isn't gravity. What they've lost is the sensation of gravity. They've lost the push of a floor beneath their feet. They've lost the signal that their body uses to determine which way is down. Without that signal, up and down simply cease to exist as meaningful concepts. Astronauts who have lived on the station report this disorientation vividly. In the early days of a mission, many astronauts feel confused and slightly nauseated. Their brains are screaming that something is wrong because for the first time in their lives, the vertical axis has vanished. There is no up. There is no down. Every direction feels the same. You can orient yourself so that your head points toward Earth, or away from Earth, or sideways relative to Earth, and nothing in your body tells you that any of those orientations is more correct than the others. They're all equally valid. They're all equally arbitrary. Mission designers at NASA understood this problem from the very beginning. When they built the interior of the International Space Station, they deliberately painted certain surfaces darker colors and designated them as the floor. Other surfaces were lighter and called the ceiling. This labeling was entirely for the psychological comfort of the crew. There is nothing about the physics of the station that makes one wall the floor and another the ceiling. The labels are a human decision, an attempt to recreate the sense of up and down that our brains desperately want, but that the environment no longer provides. Different modules of the station don't even agree. Walk from one module to another, and the floor might become a wall. The ceiling of one section might be the floor of the next. Astronauts learn to adapt. They stop relying on up and down and start using other reference points. They say things like toward the Earth-facing port, or toward the forward end of the station. They replace absolute vertical directions with relative spatial descriptions. Because in orbit there is no absolute vertical. And this is just in Earth orbit. We're only 400 kilometers above the surface. We haven't even left our own planet's neighborhood yet. Already, up has dissolved. Now let's go further. Let's visit other worlds and see what up means there. On the moon, gravity exists, but it's much weaker. The moon has only about 1/6 of Earth's surface gravity. An astronaut standing on the moon feels a clear downward pull, but down points toward the center of the moon, not toward the center of the Earth. The moon's down and Earth's down point in entirely different directions, because the two bodies are separated by about 384,000 kilometers, and they are constantly moving relative to each other. When the Apollo 11 astronauts stood on the lunar surface and looked up, they could see the Earth hanging in the black sky. From their perspective, Earth was off to one side or overhead, depending on where they were on the moon and what time it was. Earth was not down. Earth was not below them. Earth was just somewhere over there, a beautiful blue marble in the sky. Down was beneath their boots, toward the moon's center. On Mars, the same thing happens with a different direction. Mars has about 38% of Earth's surface gravity. Stand on Mars and down points toward the center of Mars, which is in an entirely different direction than down on Earth or down on the moon. The three directions have nothing to do with each other. They are determined entirely by which massive body you happen to be standing on. On Jupiter's moon, Europa, down points toward Europa's center. On Saturn's moon, Titan, it points toward Titan. On the dwarf planet Ceres in the asteroid belt, it points towards Ceres, though very weakly since Ceres is small, and its gravity is only about 3% of Earth's. Every single world in the solar system has its own local definition of down, and therefore its own local definition of up. And none of these definitions agree with each other. This isn't a small discrepancy. These aren't slightly different versions of the same direction. These are completely independent directions that point all over the place depending on where each world happens to be in its orbit at any given moment. The moon's up right now might point vaguely toward the constellation Orion. In about 14 days, when the moon has moved to the other side of its orbit, the moon's up from the same spot on its surface will point in a completely different direction. These directions are constantly changing as the worlds move through space. There is nothing permanent about any of them. They are all local, all temporary, and all defined by the accident of where mass happens to be. And this brings us to perhaps the deepest point of all. Gravity doesn't just create a direction. It creates the illusion that the direction it creates is the only direction. When you stand on Earth, gravity feels absolute. It feels like a fact about the universe, not a fact about your location. But it is a fact about your location. Move to a different location, a different planet, a different moon, and gravity provides a completely different down. Stand on no surface at all, float freely in the void between worlds, and gravity provides no down whatsoever. The feeling of absolute direction that seems so real, so unquestionable, so fundamental to your experience of reality is entirely manufactured by the local gravitational field of whatever you're standing on. Remove that gravitational field, and the feeling vanishes as completely as a dream vanishes when you wake up. This has implications far beyond physics. For thousands of years, humans assumed the universe had a natural vertical structure. The heavens were above, the underworld was below. Earth sat in the middle, with a clear top and a clear bottom. This wasn't just mythology, it was philosophy. Aristotle taught that heavy elements like earth and water naturally move downward toward the center of the universe, while light elements like fire and air naturally move upward. This framework made intuitive sense because it matched what people experienced. Rocks fall, flames raise. The universe seemed to have a built-in vertical hierarchy. But what Aristotle didn't know, what nobody could have known until we had the tools to measure and observe, is that this apparent hierarchy is entirely local. It's a product of standing on one particular planet with one particular gravitational field. Move to a different planet and the hierarchy changes. Move away from all planets and the hierarchy disappears entirely. There is no center of the universe for heavy things to fall toward. There is no cosmic above for light things to rise into. There is only mass, and the curvature of space that mass creates, bending the paths of nearby objects and generating the sensation we call weight. Now, you might be thinking, fine, there's no absolute up on a planet's surface because planets are round. But what about the solar system itself? The planets orbit the sun in roughly the same flat plane. Surely we can define up as the direction away from that plane. Surely once we zoom out from individual planets and look at the solar system as a whole, a clear vertical direction emerges. This is one of the most common assumptions people make when they learn that planetary up is local. They simply move the reference outward. If up on Earth isn't universal, then maybe up, relative to the solar system, is... After all, every diagram of the solar system shows the planets lined up neatly in a flat disk. The sun sits in the center. The planets orbit around it in the same plane. It looks like a table, and up would just mean above the table. But this assumption, as intuitive as it feels, is also wrong. And understanding why it's wrong is where our journey goes next. Because the solar system's flatness, while real, is not a flaw. It's not a surface. It's not something that defines a universal up. The story of why the solar system is flat, and why that flatness tells us less about up than you might think, is far stranger and more fascinating than most people realize. The flatness of the solar system is a consequence of how it formed, a fingerprint of angular momentum preserved across 4.5 billion years. It's a real physical feature, but treating it as a floor beneath which is down and above which is up is making the same mistake all over again, just at a larger scale. You're taking a local feature, the shape of one star system, and assuming it defines a universal direction. And as we're about to discover, the solar system's plane isn't even the only plane competing for the title. There are other planes, other axes, other directions that could just as easily claim to be up. And they all disagree with each other, dramatically. The solar system is flat, not perfectly flat, but strikingly close. If you could somehow travel millions of kilometers above the sun and look back down, you would see something that resembles a disk more than a sphere. The 8 planets, the asteroid belt, most of the moons, all of it arranged in a remarkably thin layer, all orbiting in roughly the same plane, all moving in the same direction around the sun. From this vantage point, the solar system would look almost two-dimensional, like a vinyl record spinning on a turntable. The sun at the center, the planets tracing circles in the same flat sheet around it. Nearly everything of importance confined to one narrow band. When most people see diagrams of the solar system, this flatness seems so natural that they never think to question it. Of course, the planets orbit in a disk. That's just how solar systems look. But stop and think about it for a moment. Why should this be the case? Space is three-dimensional. It extends equally in every direction. There is nothing about the laws of physics that forces objects to orbit in one plane rather than another. Planets could orbit at random angles, crisscrossing each other's paths in a tangled three-dimensional web. Some could orbit over the sun's poles while others circle around its equator. There is no law of nature that forbids this, and yet it doesn't happen. The planets all orbit in nearly the same plane. Why? The answer goes back 4.5 billion years, to the birth of the solar system itself. And it begins not with planets or even with the sun, but with a cloud. Before the sun existed, before any of the planets existed, there was a vast cloud of gas and dust drifting through space. This cloud was enormous, stretching across light years, composed mostly of hydrogen and helium, with tiny amounts of heavier elements. Carbon, oxygen, silicon, iron, elements that had been forged in the cores of earlier stars that had already lived their lives and exploded. This cloud was not doing anything particularly dramatic. It was just floating there in interstellar space, held together loosely by its own gravity. Then something disturbed it. Perhaps a nearby star exploded as a supernova, sending a shockwave through the region. Perhaps the cloud simply reached a critical density where its own gravity began to overwhelm the internal pressure holding it up. Whatever the trigger, the cloud began to collapse. Gravity pulled the gas and dust inward, toward the densest region at the center. As the material fell inward, the center grew denser and hotter. This was the beginning of the sun, but here is the crucial detail. The cloud was not perfectly still before it began to collapse. It had a tiny amount of rotation. Almost everything in the universe has some rotation. Clouds of gas drift and tumble and swirl, picking up slight spins from gravitational interactions with nearby objects, from the rotation of the galaxy itself, from 1,000 subtle influences. This particular cloud had a very slight spin, barely noticeable, so slow that if you were watching, you might not even detect it. But as the cloud collapsed, something remarkable happened. As the material fell inward, the rotation sped up. This is a consequence of one of the most fundamental principles in physics, the conservation of angular momentum. Angular momentum is, roughly speaking, the tendency of a rotating object to keep rotating. And the key property of angular momentum is that when a spinning object gets smaller, it spins faster. You've seen this in action if you've ever watched a figure skater perform a spin. The skater starts with arms extended, turning slowly. Then they pull their arms in close to their body, and suddenly they're spinning much faster. They didn't push off anything. They didn't add energy from an engine. They simply pulled mass closer to the axis of rotation, and the spin rate increased automatically to conserve angular momentum. The same thing happened to the collapsing gas cloud. As gravity pulled the material inward, the cloud shrank. And as it shrank, its rotation sped up. What started as an almost imperceptible drift became a measurable spin, then a significant rotation, then a rapid whirl. And this rotation had a dramatic effect on the shape of the cloud. Material falling toward the center, along the rotation axis, what you might call the top and bottom of the spinning cloud fell inward without much resistance. Gravity pulled it straight down and nothing stopped it. But material falling inward from the sides, from the equatorial region, encountered a different situation. As it fell inward and sped up, the centrifugal effect of the rotation pushed outward, resisting the inward pull of gravity. This created a balance. Material at the equator couldn't fall all the way to the center because its rotation was pushing it outward. So it settled into a stable orbit around the center instead. The result was that the cloud flattened. Material along the rotation axis collapsed quickly into the center, feeding the growing sun. Material at the equator settled into a disk. Over hundreds of thousands of years, the cloud transformed from a roughly spherical blob into a flat, spinning disk of gas and dust with a hot, dense protostar at the center. Astronomers call this structure a protoplanetary disk, or more historically, the solar nebula. The planets formed within this disk. Dust grains stuck together to form pebbles. Pebbles clumped into boulders. Boulders accumulated into planetesimals, objects kilometers across. Planetesimals collided and merged into protoplanets. And protoplanets grew into the planets we know today. Because all of this happened within a flat disk, the resulting planets all ended up orbiting in roughly the same plane. They inherited the flatness of the disk from which they were born. The plane of this disk is what astronomers call the ecliptic plane, or simply the ecliptic. It is defined by convention as the plane of Earth's orbit around the Sun. When astronomers say something is above or below the solar system, they are measuring relative to this plane. And this is where the first crack in the idea of a solar system up appears. Because the ecliptic is not some fundamental feature of the universe, it is the result of a specific historical accident, the particular rotation that one gas cloud happened to have 4.5 billion years ago. If that cloud had been rotating around a different axis, the ecliptic would be tilted differently. The planets would orbit in a different plane. The solar system's flat would point in a completely different direction. There is nothing sacred about the ecliptic. It's a consequence of initial conditions, not a law of nature. And the solar system isn't even perfectly flat. This is important. The ecliptic is a reference plane, but the planets don't all orbit exactly within it. They're close, but not exact. Mercury's orbit is tilted about 7 degrees from the ecliptic. That might not sound like much, but 7 degrees is significant when you're talking about an orbit that spans tens of millions of kilometers. Venus is tilted about 3.4 degrees, Mars about 1.8 degrees, Jupiter about 1.3 degrees, Saturn about 2.5 degrees. These are small tilts, but they're real. The planets are not all in exactly the same plane. They're clustered near the ecliptic but spread slightly above and below it, each on its own slightly tilted orbit. When you get to the outer solar system, the tilts become more dramatic. Pluto's orbit is inclined about 17 degrees from the ecliptic. That's a steep angle. Pluto spends significant portions of its orbit well above or well below the plane where the major planets travel. The dwarf planet Eris is tilted even more, about 44 degrees. Eris orbits on a path so steeply inclined that it passes far above and far below the ecliptic during each trip around the Sun, and comets are even more extreme. Short-period comets, those that orbit the Sun in less than 200 years, tend to have orbits that are at least roughly aligned with the ecliptic, though many are tilted significantly. But long-period comets, those with orbital periods of thousands or millions of years, arrive from every direction. They come from the Oort cloud, a vast spherical shell of icy objects that surrounds the solar system at enormous distances, and their orbits are oriented randomly. A long-period comet might plunge into the inner solar system from directly above the ecliptic, or from below it, or from any angle in between. When Halley's Comet returns every 75 or 76 years, it travels on an orbit inclined about 162 degrees from the ecliptic. That number is greater than 90 because Halley's Comet actually orbits the Sun in the opposite direction from the planets. It's going backward and steeply tilted. The ecliptic plane means nothing to Halley's Comet. It crosses that plane twice every orbit and pays it no special attention. So even within our own solar system, the ecliptic is not a universal organizing principle. It's a tendency, not a rule. Most of the major planets respect it approximately. Smaller and more distant objects often do not. And the comets that fall in from the Oort cloud ignore it entirely. The solar system has a preferred plane, but that plane is not a flaw. Objects routinely travel above and below it. There is no wall at the ecliptic. There is no barrier. There is no surface you would hit if you tried to cross it. It's simply a mathematical reference, a flat sheet defined by Earth's orbit that astronomers find useful for describing where things are. Now here's something that makes the situation even more complicated. The Sun itself has an equator, and that equator does not line up with the ecliptic. The Sun rotates on an axis, just as Earth does. And the Sun's equatorial plane, the plane perpendicular to its rotation axis, is tilted about 7¼ degrees relative to the ecliptic. This means that the plane defined by Earth's orbit and the plane defined by the Sun's own spin are not the same. They're close, but they disagree by more than 7 degrees. Why does this matter? Because if you wanted to define up as the direction perpendicular to the solar system's flat plane, you now have to choose which flat plane you mean. Do you mean the ecliptic, defined by Earth's orbit? Or do you mean the Sun's equatorial plane, defined by the Sun's rotation? These give you two different up directions. They're only 7¼ degrees apart, which in everyday life would be a small difference. But in a discussion about whether up is a universal direction, even a small disagreement is devastating. If up were truly universal, truly absolute, truly built into the fabric of the solar system, then all reference planes would agree. They would all point to the same up. The fact that they don't, even by 7 degrees, proves that up is a choice, not a discovery. You are selecting a reference and calling the direction perpendicular to it up. A different selection gives you a different up. Neither is more correct than the other. This might seem like a technical quibble, but it's actually the core of the entire issue. The whole reason people think the solar system has an up is that it's flat. The flatness suggests a plane, and a plane suggests a perpendicular direction that feels like up. But the solar system contains multiple planes that don't agree with each other. The ecliptic plane, the Sun's equatorial plane, the invariable plane, which is defined by the total angular momentum of the entire solar system and is tilted about 1½ degrees from the ecliptic. Each of these planes is real, each is physically meaningful, and each gives you a slightly different up. If the solar system had a true absolute up, all of these planes would be parallel. They would all agree. The fact that they don't means that up relative to the solar system is a convention, not an absolute. Now, can a spacecraft travel above the ecliptic? Absolutely. It is physically possible, and it has been done. In 1990, the European Space Agency and NASA launched a spacecraft called Ulysses. Its mission was to study the sun from above and below, to observe the sun's poles and the solar wind at high latitudes, regions that had never been studied before because every previous solar mission had stayed near the ecliptic plane. But getting Ulysses above the ecliptic was not simple. You might think it would be easy. Just point the rocket upward and go. But orbital mechanics does not work that way. When a spacecraft launches from Earth, it inherits Earth's orbital velocity, about 30 kilometers per second, directed along the ecliptic. To leave the ecliptic, the spacecraft doesn't just need to go up, it needs to change the direction of its orbital motion. It needs to tilt its orbit so that part of the orbit rises above the ecliptic and part dips below, and changing orbital direction requires energy. A lot of energy. In fact, changing the inclination of an orbit, tilting it relative to the ecliptic, is one of the most energy-expensive maneuvers in spaceflight. It takes more fuel to tilt an orbit by 90 degrees than it does to escape the solar system entirely. Think about that for a moment. It is easier to leave the solar system altogether than it is to fly directly over the sun's north pole from Earth's orbital distance. The reason is that the spacecraft already has enormous sideways velocity from orbiting the sun. To go perpendicular to the ecliptic, you have to cancel out that sideways velocity and replace it with the velocity in a new direction. This requires a change in velocity called delta V in engineering terms that is enormous. Ulysses solved this problem by using Jupiter. The spacecraft was launched toward Jupiter, which is about 5 times farther from the sun than Earth is. When Ulysses arrived at Jupiter in 1992, it flew close to the giant planet and used Jupiter's gravity to fling it out of the ecliptic plane. Jupiter's immense gravitational pull bent Ulysses' trajectory, redirecting it into an orbit that passed over the sun's south pole, and then swinging back around over the sun's north pole. Without Jupiter's assist, Ulysses could never have achieved this orbit. No rocket we have ever built could have provided enough delta V to tilt the orbit that steeply from Earth alone. The spacecraft needed the gravitational muscle of the largest planet in the solar system to do what no engine could. Ulysses spent the next 17 years orbiting the sun on this high inclination path, passing over the poles roughly every 6 years, sending back data about the solar wind, the sun's magnetic field, and the properties of space above and below the ecliptic. It was a triumph of engineering and creativity, and it proved beyond any doubt that spacecraft can travel above the ecliptic. There is no barrier, there is no wall, there is no physical obstacle preventing a spacecraft from flying over the sun's poles, far above the plane where the planets orbit. The ecliptic is not a cage, but here is the crucial point. Ulysses did not discover up. It did not find a universal direction when it flew over the sun's poles. It simply left one plane and entered a region of space that is above that plane. Above the ecliptic is a meaningful description, in the same way that north of the equator is a meaningful description on Earth. But neither phrase identifies a cosmic up. Saying something is above the ecliptic tells you where it is relative to a specific reference plane. It does not tell you that the thing is closer to some universal ceiling. There is no universal ceiling. The Voyager spacecraft illustrate this in a different way. Voyager 1 and Voyager 2 were launched in 1977. After completing their tours of the outer planets, both spacecraft continued outward on trajectories that are carrying them away from the Sun and out of the solar system entirely. Voyager 1 is currently traveling in a direction that takes it above the ecliptic plane, heading roughly toward the constellation Ophiuchus. Voyager 2 is heading below the ecliptic, roughly toward the constellation Pavo. The two spacecraft, launched from the same planet in the same year, are heading in nearly opposite vertical directions relative to the ecliptic. One is going up, the other is going down, and neither direction is more correct or more meaningful than the other. They're just going where their trajectories carry them, shaped by the gravitational assist they received from the planets they visited decades ago. Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively, are also leaving the solar system on different trajectories. Pioneer 10 heads roughly in the direction opposite to the Sun's motion through the galaxy. Pioneer 11 heads in roughly the direction of the Sun's motion, again, different directions, none of them up in any absolute sense. All of these spacecraft can leave the ecliptic. All of them can travel above it or below it. The ecliptic does not hold them in place. It does not restrain them. It is not a flaw. But leaving the ecliptic does not mean traveling upward in any cosmic sense. It just means moving away from one particular plane. A plane defined by the orbit of one particular planet around one particular star. Move to a different star system, and the ecliptic of that system would be oriented in a completely different direction. What counts as above in our solar system might be sideways or below in another. The ecliptic is local. It is specific. It belongs to our sun and our planets and our history. It says nothing about the rest of the universe. And this is where the problem deepens. Because you might now be thinking, fine, the ecliptic is local. The sun's equatorial plane is local. Individual planets define their own local up. But surely, at some larger scale, there must be a direction that everything agrees on. What about the galaxy? The Milky Way is a flat disk of stars, much like the solar system is a flat disk of planets. Surely the plane of the galaxy defines a real up. Surely galactic north, the direction pointing away from the top of the Milky Way's disk, is something close to a universal vertical direction. This is where the story takes its most surprising turn. Because galactic north is a real thing. Astronomers have defined it precisely. It points toward a specific spot in the sky, but it does not agree with the ecliptic north. Not even close. The angle between the ecliptic plane and the galactic plane is about 60 degrees. 60 degrees, that's not a small discrepancy. That's a massive tilt. If you imagine the solar system as a coin lying flat on a table, the galaxy's disk would be tilted like a coin leaning against a wall at a steep angle. The two planes are dramatically misaligned. Ecliptic north points in one direction, galactic north points in a very different direction. And both of them are supposedly up. This means that if you define up as perpendicular to the ecliptic, you're pointing in one direction. If you define up as perpendicular to the galactic plane, you're pointing 60 degrees away. These are not slightly different versions of the same direction. These are fundamentally different directions, and both are equally valid. Both are based on real physical structures. Both are used by real scientists for real purposes, and they disagree completely about which way is up. Which one is right? Neither. Both are conventions. Both are useful. Neither is universal. And this disagreement, This 60-degree gap between two perfectly reasonable definitions of up is the clearest proof yet that up is not an inherent feature of the universe. It's something we define. We choose a reference, a plane, an axis, and we call one direction along that axis up. Change the reference, and up changes with it. The universe itself doesn't care. It doesn't have a preference. It doesn't have an opinion about which plane should define the vertical. It just has mass and motion and geometry, and we impose our labels on top of that. The solar system's flatness is real. The ecliptic is useful. Spacecraft can travel above it and below it, but none of this brings us any closer to a universal up. The ecliptic is one reference plane among several in our own solar system, and it disagrees spectacularly with the galactic plane that surrounds it. And as we're about to discover, even the galaxy's own definition of up isn't the final word. Because there are even larger structures out there, with their own planes, their own axes, their own claims on which direction is north. And they don't agree with the galaxy either. The deeper we look, the more ups we find. And the more ups we find, the clearer it becomes that none of them is the real one. At this point in our journey, we've arrived at a striking fact. The plane of the solar system and the plane of the galaxy are tilted about 60 degrees from each other. Two perfectly real, perfectly physical structures define two completely different versions of up. And now we need to sit with that fact and explore it fully. Because this disagreement between directions is not some minor technicality buried in an astronomy textbook. It is the key to understanding why absolute up does not exist. And to see this clearly, we need to look at every major north that astronomers have ever defined and watch them argue with each other. Let's start with the one you know best. Earth's north. Every school child learns that Earth has a North Pole and a South Pole. The axis connecting these two poles is Earth's rotational axis. Earth spins around this axis once every 23 hours and 56 minutes. And the direction of this spin defines geographic north and south. North is the direction along the axis that corresponds to counterclockwise rotation when viewed from above. If you hovered far above the North Pole and looked down, you would see the planet spinning counterclockwise beneath you. That's the convention. Counterclockwise from above means that direction is north. This axis doesn't point straight up and down relative to Earth's orbit. It's tilted. Earth's rotational axis leans about 23.4 degrees away from the perpendicular to the ecliptic plane. This tilt is the reason we have seasons. When the northern hemisphere tilts toward the sun, it's summer in the north and winter in the south. 6 months later, the tilt points the northern hemisphere away from the sun, and the seasons reverse. This 23.4 degree tilt has shaped virtually every aspect of life on Earth. Agriculture, migration patterns, cultural traditions, weather systems, all of them depend on this tilt. It feels fundamental. It feels like it must be significant on a cosmic scale, but it isn't. Earth's axial tilt is an accident. It's believed to be the result of a collision billions of years ago, when a Mars-sized body slammed into the early Earth. The impact knocked our planet's spin axis to its current angle and blasted enough material into orbit to form the Moon. If that collision had come from a slightly different direction, the tilt would be different. Seasons would be different. Climate would be different. History would be different. The tilt is not a law of physics. It's a scar from a specific impact that happened to occur at a specific angle in the chaotic early solar system. Nothing about it is universal. Right now, Earth's North Pole points approximately toward the star Polaris, which is why Polaris is called the North Star. If you stand in the northern hemisphere and look toward Polaris, you're looking along the direction of Earth's rotational axis. Polaris appears to hang motionless in the sky while all other stars rotate around it, tracing circles as the night progresses. This makes Polaris incredibly useful for navigation. Sailors and travelers have relied on it for centuries to find north. It feels permanent. It feels like it has always been there and always will be. But it hasn't, and it won't. Earth's rotational axis is not fixed in space. It wobbles. Slowly, steadily, the axis traces a large circle in the sky over a period of about 26,000 years. This motion is called precession, and it happens because of the gravitational tug of the sun and moon on Earth's equatorial bulge. Earth is not a perfect sphere. It bulges slightly at the equator because of its rotation. The sun and moon pull on this bulge, and because the pull is slightly uneven, it causes the axis to precess, to slowly change the direction it points, like a spinning top, wobbling as it slows down. 26,000 years ago, the North Pole pointed toward a completely different part of the sky. Polaris was not the North Star. About 5,000 years ago, when the ancient Egyptians were building the Great Pyramids, the North Pole pointed roughly toward a star called Thuban in the constellation Draco. The Egyptians knew Thuban as their pole star. About 12,000 years from now, the axis will point toward Vega, one of the brightest stars in the sky, and Vega will become the North Star. 12,000 years after that, the axis will have completed its circuit and returned to pointing near Polaris again. This cycle repeats endlessly, the axis sweeping through a full circle every 26,000 years. Earth's north is not even fixed. It moves. It wanders among the stars on a timescale that is long by human standards, but short by cosmic ones. And there's an even subtler wobble on top of precession. It's called nutation, a small oscillation in the axis caused by the changing geometry of the moon's orbit. Nutation adds a tiny shake to the larger precessional sweep, and beyond nutation, there are even tinier perturbations caused by the gravitational pull of other planets. Earth's rotational axis is not pointing in a single steady direction. It's wobbling, oscillating, and drifting, constantly changing where it aims among the stars. The north, defined by Earth's axis, is a moving target, always shifting, never fixed. Now let's set Earth's north aside and look at the next candidate. Ecliptic north. This is the direction perpendicular to the ecliptic plane, the plane of Earth's orbit around the Sun. It's defined using the same right-hand convention. If you curl the fingers of your right hand in the direction the planets orbit, counterclockwise when viewed from above, your thumb points toward ecliptic north. Ecliptic north points toward a spot in the constellation Draco, the same sprawling constellation where the star Thuban resides, the star that was the Egyptian pole star 5,000 years ago. This is a coincidence, not a deep connection. But what matters is that ecliptic north and Earth's geographic north do not point in the same direction. They are separated by 23.4 degrees, the same angle as Earth's axial tilt. This means that if you're standing on Earth and pointing toward Polaris, you are pointing 23.4 degrees away from where ecliptic north is. If you are somehow hovering above the solar system and pointing toward ecliptic north, you would not be pointing toward Polaris. You'd be pointing nearly a full handspan away from it in the sky. Two definitions of north, both real, both physical, and they disagree by 23.4 degrees. Already, we have a problem. Next is solar north. The sun rotates on its own axis, completing one rotation roughly every 25 days at its equator. Like Earth, the sun's rotational axis defines a north and south pole. Solar north is the direction along this axis corresponding to the sun's counterclockwise rotation. But the sun's equatorial plane is tilted about 7.25 degrees relative to the ecliptic. This means solar north is 7.25 degrees away from ecliptic north. It's a smaller disagreement than the one between ecliptic north and Earth's north, but it's still a disagreement. 3 definitions of north in our own solar system, and none of them align perfectly. Let me be precise about this because it matters. Earth's geographic north, ecliptic north, and solar north point in 3 different directions. They're all within about 23 degrees of each other, which might seem close, but if up were an absolute direction, these 3 should agree perfectly. They should all point to exactly the same spot in the sky. The fact that they don't, even by a few degrees, demonstrates that none of them is the real, absolute up. Each is defined by a different physical reference: Earth's spin, Earth's orbit, the sun's spin, and each gives a different answer. Now, let's look at what happens when you ask the same question to the other planets. Because every planet in the solar system has its own rotational axis, its own north, and they all point in wildly different directions. Mars has an axial tilt of about 25 degrees, similar to Earth's. So Martian north points in a roughly similar direction relative to Mars's orbital plane. But roughly similar is not the same. And because Mars orbits the Sun at a different distance, and with a slightly different orbital inclination, the actual direction of Martian north in space is different from Earth's north. Jupiter's axis is tilted only about 3 degrees from the perpendicular to its orbital plane. Jupiter is nearly upright. Its north pole points in a direction that is close to ecliptic north, but not identical. Saturn has a tilt of about 27 degrees. Neptune has a tilt of about 28 degrees. Each planet's north is unique, tilted at its own angle, pointing in its own direction, defined by its own rotation. And then there's Uranus. Uranus is tilted about 98 degrees from the perpendicular to its orbit. It is essentially lying on its side. While most planets spin roughly upright like tops, Uranus rolls along its orbit like a ball. Its north pole sometimes points almost directly at the Sun. This extreme tilt is thought to have been caused by a collision with an Earth-sized object early in the solar system's history. Uranus's north is roughly in the plane of the ecliptic, pointing in a direction that is nearly perpendicular to where most other planets' north poles point. If you asked Uranus which way is up, its answer would be almost completely sideways compared to Earth's answer. Venus is even stranger. Venus rotates backward. While most planets rotate counterclockwise when viewed from above their north poles, Venus rotates clockwise. Its axial tilt is about 177 degrees, which is mathematically equivalent to being nearly upside down and spinning in the opposite direction. Venus's north pole, if you define it the way astronomers typically do as the pole above which the planet rotates counterclockwise, is actually pointing in almost the opposite direction from most other planets' north poles. So in our solar system alone, the planets define at least 8 different norths, 8 rotational axes, pointing in 8 different directions, none of them aligned. Mercury's north, Venus's north, Earth's north, Mars's north, Jupiter's north, Saturn's north, Uranus's north, Neptune's north. They're all different. They all disagree. And if you add the sun's north and ecliptic north, you have 10 competing definitions, and not a single pair of them matches exactly. Now let's go bigger, much bigger. Let's leave the solar system entirely and look at the Milky Way. Our galaxy is a flat disk of stars, gas, and dust, roughly 100,000 light years across and about 1,000 light years thick. Like the solar system, the Milky Way has a plane defined by this disk and a direction that astronomers call galactic north, perpendicular to the disk. Galactic north points toward a region in the constellation Coma Berenices, near the boundary with the constellation Leo. This direction has been measured with high precision using observations of stars, gas clouds, and the distribution of matter throughout the galaxy. And here is where the disagreement becomes dramatic. Galactic north is tilted about 60 degrees from ecliptic north, not 7 degrees, not 23 degrees, 60 degrees. That is an enormous angle. If you point one arm toward ecliptic north and the other toward galactic north, the angle between your arms would be wider than the corner of an equilateral triangle. These two directions have almost nothing to do with each other. This means the plane of the solar system and the plane of the galaxy are dramatically misaligned. If you picture the solar system as a coin lying flat on a table, the galaxy's disk would be tilted, like a coin propped up at a steep angle, almost leaning against the wall. The planets orbit in one plane, and the stars of the Milky Way are arranged in a completely different plane. There is no relationship between these two orientations. The solar system's ecliptic was determined by the rotation of one collapsing gas cloud 4.5 billion years ago. The galaxy's disk was determined by the rotation of a much larger structure over a much longer timescale. The two had nothing to do with each other. Their alignment, or rather their dramatic misalignment, is purely random. But it gets worse. Because even galactic north, which might seem like a stable and well-defined direction, hides a complication that most people never hear about. The Milky Way's disk is not perfectly flat. It's warped. Imagine a vinyl record that someone has gently twisted, so that one edge curves slightly upward, and the opposite edge curves slightly downward. That is roughly what the Milky Way looks like when viewed edge-on. The inner regions of the galaxy, where the sun sits, are relatively flat, but as you move outward toward the edges of the disk, the plane of the galaxy bends. On one side, the outer disk curves above the midplane defined by the inner galaxy. On the other side, it curves below. This warp has been known to astronomers for decades. It was first detected through radio surveys of hydrogen gas, which traces the structure of the galactic disk far beyond where optical telescopes can see through the dust. The hydrogen maps showed clearly that the outer disk doesn't stay in the same plane as the inner disk. It bends gradually at first, and then more dramatically at the galaxy's outermost reaches. The warp extends for tens of thousands of light years, lifting one side of the outer galaxy above the midplane and pushing the other side below it. More recently, the Gaia spacecraft, which is mapping the precise positions and motions of nearly 2 billion stars in the Milky Way, has confirmed and refined this picture. Gaia's data show that the warp is real, significant, and not static. The warp itself is precessing, slowly rotating around the galaxy like a wobble in a spinning top, completing one full precession cycle every 600 to 700 million years. The galactic disk is not just bent, It's a bent disk that's slowly twisting over time. What does this mean for galactic north? It means that galactic north is not the same direction everywhere in the galaxy. In the inner regions near the Sun, the disk is relatively flat, and galactic north points roughly toward Coma Berenices, as astronomers have defined it. But out at the edges of the galaxy, where the warp is significant, the local plane of the disk is tilted relative to the inner plane. A star on the warped outer edge of the galaxy would define its own local galactic plane, perpendicular to the disk at that location, and that local plane would be tilted relative to the plane defined at the Sun's position. The local galactic north of that distant star would point in a slightly different direction than our galactic north. This is a remarkable echo of what we found inside the solar system. In the solar system, the ecliptic is not perfectly flat because the planets' orbits are tilted at different angles. In the Milky Way, the galactic plane is not perfectly flat because the disk itself is warped. In both cases, the reference plane that seems so clean and definitive on a diagram turns out to be approximate, local, and slightly different depending on where you are. Even within the single structure, up shifts. Even the galaxy cannot provide a single, consistent, universal direction. The Milky Way tried to give us galactic north, and even that turns out to depend on where in the galaxy you're standing. Astronomers use different coordinate systems depending on what they're studying, and each system defines north differently. When studying the planets, they use ecliptic coordinates, with ecliptic north as the reference. When mapping the position of stars as seen from Earth, they use equatorial coordinates, based on a projection of Earth's equator onto the sky. In this system, north is the direction of Earth's rotational axis toward Polaris. When studying the structure of the Milky Way, they use galactic coordinates, with galactic north pointing toward Coma Berenices. And when studying the cosmic microwave background or the large-scale structure of the universe, they use yet another coordinate system. Each of these systems is useful for its purpose. Each makes certain calculations easier. Ecliptic coordinates are natural for planetary science because the planets orbit near the ecliptic. Equatorial coordinates are natural for observational astronomy because telescopes are mounted on Earth and follow the sky as it rotates around Earth's axis. Galactic coordinates are natural for studying the galaxy because they align with the galaxy's structure. No system is more real than the others. They're all mathematical frameworks, human inventions imposed on a universe that does not come with built-in graph paper. And every single one of them defines a different north, a different up. They all work. They're all correct within their own framework, but they disagree with each other about which direction is up, and the disagreements are enormous, from 7 degrees to 23 degrees to 60 degrees. Now, you might ask whether there is some even larger structure that could settle the debate. The Milky Way defines galactic north, but the Milky Way is just one galaxy. It belongs to a larger structure, the local group of galaxies, which belongs to the Virgo supercluster, which belongs to an even larger structure called Laniakea. Do these larger structures have a preferred plane, a preferred up? In a loose sense, some of them do. The local group has a rough plane defined by the positions of its largest members, the Milky Way, Andromeda, and Triangulum. But this plane is poorly defined because the local group is small and its galaxies are not neatly arranged. The Virgo supercluster has a flattened shape, and you could define a direction perpendicular to its long axis. Laniakea has a general direction of flow, toward the region called the Great Attractor. But none of these directions agree with galactic north. They all point in different directions, and they're all defined by specific local structures, not by universal features of the cosmos. Here is a comparison that might drive the point home. At the very center of our galaxy sits a supermassive black hole called Sagittarius A star. This black hole has a mass of about 4 million times the mass of the Sun, and it is spinning. Its spin axis defines yet another north, but the spin axis of Sagittarius A star is not aligned with galactic north. The black hole's spin is tilted relative to the galactic disk. Even the most massive, most central object in our galaxy disagrees with the galaxy's own definition of up. And the black hole at the center of M87, a giant galaxy in the Virgo cluster, has its own spin axis that points in yet another direction. Its spin axis is dramatically tilted relative to M87's disk, and relative to our galaxy's disk, and relative to the ecliptic, and relative to Earth. Every massive spinning object in the universe defines its own north, and no two of them need to agree. By now, the pattern should be clear. There's no single direction in space that everything calls north. There is no universal up. There are only local ups, defined by local objects. Earth's rotation defines one up. The Sun's rotation defines another. The ecliptic defines a third. The galaxy defines a fourth. Other galaxies define their own, and all of these directions point in different places. This is not a failure of measurement. This is not something that better telescopes or better mathematics will fix. The disagreement is real and fundamental. It exists because up is not a property of space. It's a property of a reference frame. Choose a different reference frame and you get a different up. The universe does not prefer one reference frame over another. They're all equally valid, and therefore all definitions of up are equally valid and equally arbitrary. Consider what this means for a spacecraft traveling through the solar system. Mission controllers choose a coordinate system for navigation. They might use ecliptic coordinates when planning a trajectory to Mars, or equatorial coordinates when pointing antennas at ground stations. When the Voyager 1 spacecraft sends data back to Earth, it aims its antenna toward Earth. Is Earth up from Voyager 1's perspective? No. Earth is just a direction. The direction where the receiver happens to be. If the spacecraft rotated to aim its antenna at a different star, that star would now be in the same relative position. Nothing about the spacecraft's physics would change. Only the label would change. Astronauts experience this directly. On the International Space Station, as we saw earlier, there is no felt up or down. But the station's designers had to pick an orientation for the interior, which walls would be labelled floor and which would be labelled ceiling. They chose to orient the station so that the labelled floor generally faces toward Earth. This is a human psychological comfort, not a physical necessity. The station could be flipped upside down and nothing about its orbit, its speed, or its physics would change. The only thing that would change is which labels are on which walls. Up and down inside the station are conventions. Stickers on surfaces, not features of the universe. And this connects to something deeper about how orientation works in space. A spacecraft can rotate freely. It can point its nose toward the sun, toward the galactic center, toward Polaris, toward a random patch of darkness between galaxies. It can aim in any direction whatsoever. But pointing in a direction does not make that direction up. Orientation is not the same as discovering a preferred direction. When a spacecraft rotates to face the sun does not become up. When it rotates to face the galactic center does not become up. The spacecraft has simply aimed itself. It has chosen an orientation. The universe didn't provide that orientation. The spacecraft's navigation system did. This distinction between choosing a direction and discovering a direction is the heart of the entire issue. On Earth's surface, it genuinely feels like we discovered up. We didn't choose it. Gravity chose it for us. It imposed a direction on us whether we wanted it or not. We can't opt out of gravity. We can't decide that up is sideways. Gravity enforces a specific vertical axis, and we have no say in the matter. This experience is so overwhelming, so total, so constant that we naturally assume up exists independently of us. We assume it's out there, built into the fabric of things, waiting to be found. But gravity is local. Its direction depends on where you are and what massive objects are nearby. Away from any massive object, in the deep void between galaxies, there is no gravitational pull in any particular direction. There is no down to fall toward, and therefore there is no up to point away from. A person floating in intergalactic space would feel no preferred direction whatsoever. Every direction would feel exactly the same as every other direction. There would be nothing in their physical experience to distinguish up from down, from left, from right. All directions would be identical. Astronomers studying far-off galaxies face this constantly. When they observe a distant spiral galaxy, they see it at whatever angle it happens to be tilted relative to our line of sight. Some galaxies appear face-on, showing their beautiful spiral arms spread out like pinwheels. Others appear edge-on, looking like thin lines of light. The orientation is random. There's no rule that says galaxies should face a particular direction. They're tilted every which way, their disks pointing randomly through space. Each one has its own north, defined by its own rotation, and those north point in every conceivable direction. If you catalogue the north poles of every galaxy in the observable universe, you would find them scattered uniformly across the sky. No preferred direction, no clustering. No hint that one direction is more north than any other. This observation has been confirmed statistically. Astronomers have looked at the orientations of millions of galaxies and found that they are randomly distributed. There is no direction in space that galaxies preferentially align with. There's no cosmic up that galaxies tend to point toward. They spin in every direction, their axes scattered randomly, each one a local definition of north that says nothing about the universe as a whole. And this randomness is exactly what we would expect if there is no universal up. If there were a preferred direction in the universe, if the cosmos really did have a built-in vertical axis, we would expect to see its signature. Galaxies might tend to align with it. The cosmic microwave background might be brighter in one direction. Matter might distribute itself differently along the preferred axis compared to perpendicular to it. But none of these signatures appear. As far as every observation can tell, the universe treats all directions equally. No direction is special, no direction is preferred, no direction is up. What we have instead is a hierarchy of local reference frames. Each one useful, each one real within its own context, and none of them universal. Earth's gravity defines down when you're standing on Earth. The ecliptic defines a useful reference plane for studying the solar system. The galactic plane defines a useful reference for studying the Milky Way. Larger structures define their own references, but none of these frames extends to the entire universe. None of them is the final word. Each is superseded by a larger structure that defines a different direction, and the chain never reaches an endpoint where a universal up is finally established. This is what makes the question in our title so fascinating and so deceptive. When people hear that you can't go up in the solar system, they imagine a physical barrier, something preventing spacecraft from traveling above the planets. But there is no barrier. Spacecraft can and do travel above the ecliptic. The impossibility is not physical, it's conceptual. You cannot go up in the solar system because there is no up to go toward. Every direction that anyone has ever called up was defined by a specific local reference, and different references give different answers. There is no cosmic north. There is no absolute vertical. There is no direction that the universe itself recognizes as upward. And as we're about to see in our final exploration, this isn't just a quirk of how we measure things. It's a fundamental feature of the universe, woven into the deepest laws of physics, confirmed by the most precise observations humans have ever made. The universe is not just lacking a preferred up. It appears to actively resist having one. And understanding why will bring our journey to its conclusion. We've traveled a long road to reach this final stretch. We started on the surface of Earth, where up felt absolute, wired into reality, impossible to question. We watched that certainty dissolve in orbit, where astronauts float without any sense of vertical direction. We saw the solar system's flatness, the ecliptic plane, and learned that it is a useful reference, but not a flaw. We counted the competing norths: Earth's north, ecliptic north, solar north, galactic north, and watched them disagree with each other by as much as 60 degrees. At every scale, the same lesson repeated. Up is local. Up is defined by whatever reference you choose, and different references give different answers. Now we need to ask the deepest version of the question. Forget planets, forget the solar system, forget even the galaxy. Does the universe itself, at the very largest scale, have a preferred direction? Is there some cosmic axis, some universal vertical, some direction that everything in existence would agree is up, if only we could find it? The answer, supported by every observation and every experiment we have ever conducted, is no. Let's start with a spacecraft in deep space, far from any star, any planet, any gravitational influence. Imagine this ship drifting in the void between galaxies, millions of light years from the nearest significant mass. Inside, the crew floats weightless. There is no gravitational pull from any direction. Their instruments detect no force drawing them toward any particular point. The darkness outside looks the same in every direction. Stars and galaxies are scattered across the sky, but they're scattered roughly uniformly. No direction looks special. No direction looks different. Now the crew decides to orient the ship. The pilot fires small thrusters and rotates the spacecraft so that its nose points toward a particular distant galaxy. Is that direction now up? Obviously not. The pilot could just as easily have pointed the nose in the opposite direction, or sideways, or at any random angle. The ship's orientation is a choice. It's a setting in the navigation computer. It tells you which way the ship is facing, not which way is up. The universe didn't tell the pilot to point that way. The pilot told the ship to point that way. And if the pilot rotates the ship to face a completely different direction, nothing about the physics changes. The ship doesn't suddenly start falling. The crew doesn't feel any force. The instruments don't register anything different. The universe is entirely indifferent to how the spacecraft is oriented. This is a crucial distinction. Orientation is not the same as direction. A compass on Earth points north because Earth's magnetic field creates a real, detectable asymmetry. The magnetic field breaks the symmetry of directions. North is physically different from south because the field lines point in a specific way. But in deep space, away from any local magnetic field or gravitational source, there is no such asymmetry. No direction is physically different from any other. You can aim a spacecraft any way you want, but you haven't discovered anything. You've just made a choice. Now, is it possible that the universe has some subtle asymmetry that we haven't detected yet? Some faint preferred direction hiding in the data? Scientists have looked for this. They've looked hard. And the most powerful tool they have for checking is the cosmic microwave background, the faint glow of radiation left over from the early universe. The cosmic microwave background is, in a sense, the oldest light in existence. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space for the first time. Before that moment, the universe was a hot, dense fog of particles and radiation, opaque to light. After that moment, the fog cleared and photons began streaming in every direction. Those photons have been traveling ever since, for about 13.8 billion years, cooling as the universe expanded, stretching from the short wavelengths of visible light to the long wavelengths of microwaves. Today, they arrive at our telescopes from every direction in the sky, a faint whisper of the universe's infancy. And here is what makes the cosmic microwave background so important for our question. It is almost perfectly uniform. When you measure the temperature of this radiation, the temperature that tells you how energetic the photons are, you find that it is the same in every direction. The temperature is about 2.725 Kelvin, just a few degrees above absolute zero. And it's the same whether you look north, south, east, west, up, down, or anywhere in between. The uniformity is extraordinary. The variations are tiny, only about 1 part in 100,000. The cosmic microwave background tells us, with astonishing precision, that the universe looks the same in every direction at the largest scales. This observation is the foundation of what cosmologists call the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Homogeneous means it looks roughly the same everywhere. Isotropic means it looks roughly the same in every direction. This isn't just an assumption. It's a tested, measured, confirmed property of the real universe. 3 different satellite missions have mapped the cosmic microwave background with increasing precision. COBE, launched in 1989, made the first full-sky map and confirmed the radiation's uniformity. WMAP, launched in 2001, measured the tiny fluctuations with much greater precision, and the Planck satellite, launched in 2009, produced the most detailed map yet. All 3 missions confirmed the same result. The universe is isotropic to an extraordinary degree. What does isotropy mean for up? It means there is no preferred direction. If the universe had an up, if there was some cosmic axis that defined a universal vertical, we would expect to see its signature in the cosmic microwave background. The radiation might be slightly warmer in one direction and cooler in the perpendicular direction. The fluctuations might be slightly larger along the axis and smaller across it. The pattern of hot and cold spots might align with the preferred direction in some detectable way, but none of these signatures appear. The cosmic microwave background is the same in every direction, within 1 part in 100,000. There is no axis. There is no alignment. No direction stands out as special. Now, there is one subtle asymmetry in the cosmic microwave background that's worth addressing, because it sometimes confuses people into thinking there is a preferred direction. It's called the dipole. The cosmic microwave background is very slightly warmer in one direction, toward the constellation Leo, and very slightly cooler in the opposite direction. The temperature difference is tiny, about 0.003 of a Kelvin, but it's measurable. Does this define an up? No. The dipole exists because we are moving. The Sun, and with it the entire solar system, is not at rest relative to the cosmic microwave background. We are moving through space at about 370 kilometers per second relative to the frame in which the cosmic microwave background would appear perfectly uniform. This motion is a combination of several things. The Sun orbits the center of the Milky Way at about 230 kilometers per second. The Milky Way itself is falling toward the Great Attractor at about 600 kilometers per second as part of the larger flow within Laniakea. All of these motions add up to give us a net velocity relative to the cosmic microwave background. Because of this motion, the cosmic microwave background radiation is slightly blue shifted in the direction we're moving, making it appear warmer, and slightly red shifted in the direction we're coming from, making it appear cooler. This is the Doppler effect, the same phenomenon that makes a siren sound higher pitched when an ambulance approaches and lower pitched when it drives away. The dipole tells us which direction we're moving. It tells us our velocity relative to a particular frame of reference, but it does not define up. Moving forward is not the same as moving upward. The direction of our motion through the cosmic microwave background has nothing to do with a vertical axis. It's just the direction we happen to be traveling, shaped by the gravitational influences of structures around us, and that direction keeps changing. The Sun's orbital motion around the galaxy changes direction over hundreds of millions of years as the Sun completes its galactic orbit. The Milky Way's motion within Laniakea evolves as the gravitational landscape shifts. The dipole direction is not fixed. It's not permanent. It's not an axis of the universe. It's a snapshot of our current motion, and our current motion is just an accident of where we happen to be and what gravitational influences happen to be pulling on us right now. But the dipole is not the only feature that has tempted people into believing the universe might have a preferred direction. In the early 2000s, when the WMAP satellite produced its detailed map of the cosmic microwave background, a group of researchers noticed something unexpected. When they analyzed the larger scale patterns in the map, the broadest hot and cold regions stretching across the entire sky, those patterns appeared to line up. Not randomly, as the standard cosmological model was predicted, but along a specific axis. Even more surprising, this axis seemed to point in roughly the same direction as the ecliptic, the plane of Earth's orbit around the Sun. This was deeply strange. The cosmic microwave background is ancient light from the very beginning of the universe. The ecliptic is defined by the orbit of one small planet around one ordinary star. There should be absolutely no connection between the two. The probability of a coincidental alignment was small enough to raise eyebrows. Researchers gave the anomaly a dramatic, half-joking name. They called it the axis of evil because it seemed to threaten the cosmological principle, the foundational assumption that the universe has no preferred direction. For several years, the axis of evil generated intense debate. Some physicists speculate that it might be evidence of genuinely new physics, perhaps a sign that the universe really does have a preferred axis, or that the topology of space is more complicated than we thought. Maybe the universe is finite in some direction, and that finiteness creates an imprint in the cosmic microwave background. Maybe there is some unknown field or structure that imposes a subtle directionality on the cosmos. If any of this were true, it would have overturned one of the deepest assumptions in cosmology. It would have meant that the universe, at the very largest scale, is not truly isotropic. It would have meant there is a special direction after all. But then, the Planck satellite flew. Planck launched in 2009 and produced the most precise map of the cosmic microwave background ever made, far more detailed and more carefully calibrated than W maps. And here is what makes the story so interesting. When researchers analyzed the Planck data, the alignment did not disappear. If anything, Planck confirmed that the anomaly was real. The quadrupole and octupole of the cosmic microwave background genuinely do line up with each other and with the ecliptic direction. This was not a WMAP artifact. It was not caused by faulty instruments. It was a real feature of the oldest light in the universe. So, does this mean the universe has a preferred direction after all? The scientific consensus, even after Planck confirmed the signal, is no. The reason comes down to statistics. When you have a dataset as large and detailed as a full sky map of the cosmic microwave background, there are thousands of patterns you could look for. Alignments, asymmetries, cold spots, hot spots, correlations between different scales. If you search for enough patterns, some of them will appear significant purely by chance. This is called the look elsewhere effect. The axis of evil alignment, while real, has a probability of about 1 to 2% of occurring by random chance. That sounds small, but when you consider how many different anomalies researchers tested for, finding one at this level is not surprising. It's roughly what you would expect from a universe with no preferred direction if you look hard enough. The axis of evil is real, but it is not strong enough to overturn the cosmological principle. It sits in the ambiguous zone between interesting coincidence and genuine evidence. Most cosmologists treat it as a curiosity, something worth monitoring as better data arrives, but not a reason to conclude that the universe has a preferred axis. The universe, as best we can measure, remains isotropic. The cosmological principle survived its most dramatic challenge, not because the challenge vanished, but because it wasn't quite strong enough to win. Physicists have also searched for other kinds of asymmetry. They've looked for patterns in the distribution of galaxies, hoping to find some preferred axis or plane at the largest scales. They've examined the polarization of the cosmic microwave background for signs of a universal rotation. They've studied the orientations of distant quasars, blazars, and radio galaxies. In every case, the result is the same. No preferred direction, no cosmic axis, no universal up. The universe, as far as we can tell, is genuinely isotropic. All directions are equal. This isotropy is not just an observation. It connects to some of the deepest principles of physics. In 1918, the mathematician Emmy Noether proved a theorem that links symmetries to conservation laws. If the laws of physics are the same regardless of where you are, then momentum is conserved. If the laws are the same regardless of when you are, then energy is conserved. And if the laws are the same regardless of which direction you're facing, then angular momentum is conserved. This last symmetry, rotational symmetry, is directly related to our question. If the universe has no preferred direction, then the laws of physics work the same no matter how you orient your experiment. You can rotate your laboratory to face any direction, and all your experiments will produce the same results. This rotational symmetry has been tested with extraordinary precision. Atomic clocks, laser interferometers, particle accelerators, all of them produce results that are independent of direction. The laws of physics genuinely don't care which way you're pointing. If the universe had a preferred up, this symmetry would be broken. Experiments conducted vertically might give different results from experiments conducted horizontally. Light might travel at slightly different speeds in different directions. The fundamental constants of nature might vary depending on orientation. None of these effects have ever been observed. The rotational symmetry of physical law is one of the most precisely tested properties in all of science, confirmed to extraordinary accuracy. The universe does not have a preferred direction. Period. Let me bring this back to the title of our exploration. Why is it actually impossible to go up in the solar system? Not because spacecraft can't travel above the planets. They can. We've done it. Not because there's a wall or a barrier, the ecliptic plane. There isn't. Not because some physical force prevents you from leaving the disk of the solar system. No such force exists. It's impossible to go up in the solar system because the solar system does not have an up. There is no direction that is universally, absolutely, objectively upward. Every direction that has ever been called up was defined relative to a local reference, a planet's surface, an orbital plane, a galaxy's disk, a rotational axis. And every one of these references gives a different answer. Earth says up is one direction. The ecliptic says it's another. The sun says it's a third. The galaxy says it's a fourth. And the universe as a whole says nothing at all. It has no preference. It treats all directions equally. You can travel above the ecliptic. That is a real, meaningful statement. It means your position has a positive elevation relative to the plane of Earth's orbit. You can travel above the galactic disk. That too is meaningful. It means you've moved away from the plane where most of the Milky Way's stars are concentrated. But neither of these statements means you have traveled up in any absolute sense. Above the ecliptic is not the same as upward. Above the galactic plane is not the same as upward. They are descriptions of position relative to specific references, and those references do not define a universal vertical. Changing your reference changes the meaning of above. What is above the ecliptic might be sideways relative to the galactic plane, and downward relative to some other galaxy's disk. The word above has no fixed meaning in space. It's always relative, always contingent, always dependent on the framework you choose. Think about what this means for how we picture the solar system. Every diagram you have ever seen of the solar system shows the planets orbiting in a flat plane with the sun in the center. These diagrams almost always orient the plane horizontally, with the viewer looking down from above. This makes ecliptic north point up in the diagram toward the top of the page. And because we see this image over and over in textbooks, documentaries, and websites, we unconsciously internalize it. We start to believe that the solar system really does have a top and a bottom, that there really is a direction called above the solar system that corresponds to an absolute up. But the diagram's orientation is arbitrary. You could draw the same diagram with the ecliptic tilted at 45 degrees. You could draw it edge on. You could draw it upside down with ecliptic south at the top of the page. The physics wouldn't change. The orbits would be the same. The planets would be in the same relative positions. The only thing that would change is the orientation on the page, which is a choice made by the artist, not a fact about the universe. Every solar system diagram you've ever seen had its orientation chosen by a human being, and that human being could have chosen differently. The fact that most diagrams put ecliptic north at the top is a convention, inherited from centuries of map-making tradition where north goes at the top. It's a cultural habit, not a cosmic truth. The same applies to images of the Milky Way. Every artist's impression of our galaxy shows it oriented in some particular way, usually with the disk horizontal and galactic north pointing up, but the Milky Way doesn't know which way it's oriented. It doesn't have a top. It doesn't have a bottom. An artist in a different culture might orient the image differently, and neither version would be more correct than the other. There is something deeply humbling about this realization. We evolved on a world where direction mattered enormously. Falling down could kill you. Reaching up could save you. Up meant sky, sunlight, air, safety. Down meant ground, darkness, burial, danger. Our ancestors depended on their sense of direction for survival. The ability to instantly know which way is down was literally a matter of life and death. Animals that couldn't orient themselves relative to gravity didn't survive long, so evolution wired us, deeply and powerfully, to treat the vertical axis as the most important axis in the world. Up and down are the first directions we learn. They're the most instinctive directions we have. They feel more real, more fundamental, more permanent than any other spatial relationship. And that wiring is so strong that even when we leave the surface, even when we intellectually understand that up is local, some part of our brain keeps insisting that there must be a real up somewhere. We keep looking for it. We keep trying to promote some local reference to universal status. First it was Earth's surface, then the ecliptic, then the galactic plane. Each time we take a local framework and try to extend it to the whole universe, and each time the universe gently but firmly tells us no. There is no preferred direction, there is no cosmic ceiling, there is no universal top. The universe has mass, it has energy, it has curvature and motion and structure at every scale. But it does not have a vertical axis, it does not have a top and a bottom, it does not have an up and a down. These concepts exist only in the presence of gravity or in the context of a chosen reference frame. Remove the gravity and remove the reference, and the concepts vanish completely. They were never properties of the universe. They were properties of our experience of the universe, shaped by the fact that we happen to live on the surface of a massive spinning ball. This might feel disorienting. It might feel like losing something. If there's no up, then how do we orient ourselves? How do we make sense of space? How do we know where we are? The answer is that we orient ourselves the same way we always have, by choosing references and sticking with them. Sailors use the stars, pilots use instruments, astronauts use mission controls, coordinate systems, Astronomers use whichever coordinate system suits the problem they're working on. None of these references is absolute. All of them are choices, but they work. They allow us to navigate, to communicate positions, to plan trajectories, to map the cosmos. We don't need an absolute up to function. We just need consistent, agreed upon references. And that's exactly what we have. There is a strange beauty in this. The universe is not a room with a floor and a ceiling. It's not a house with a top and a bottom. It's something far more interesting. It's a space that extends equally in every direction, where every point is as valid as every other, where no direction is special, where the laws of physics work the same no matter how you orient yourself. This perfect symmetry is not a limitation. It's one of the most elegant and profound features of the cosmos. The universe doesn't play favorites. It doesn't privilege one direction over another. It treats all of space, all directions, all orientations, with perfect equality. And we are the ones who impose order on this symmetry. We choose our references. We define our norths. We draw our maps with whatever orientation suits us. We label the walls of our space stations. We orient our textbook diagrams. And all of these choices are valid because none of them is claiming to be absolute. They're just useful. They're just practical. They're just human. Think about what this says about us as a species. For hundreds of thousands of years, our ancestors navigated the world using a direction they believed was absolute. Down was down. Up was up. The vertical axis was a gift from the universe, a built-in compass that never failed. And then, in the span of just a few centuries, we figured out the truth. We realized that our most trusted direction, the one we felt with every fiber of our bodies, the one that shaped our architecture and our language and our myths, was not a cosmic truth at all. It was a local phenomenon, a product of standing near a particular mass, a feeling so powerful and so consistent that it masqueraded as a fact about the universe for the entire history of human thought. And we saw through it, not through some divine revelation, not through some sudden mystical insight, but through careful observation, through mathematics, through building instruments that could measure what our senses could not. We sent spacecraft above the ecliptic and proved there was no wall. We mapped the cosmic microwave background and proved there was no axis. We tested the rotational symmetry of physical law and proved that no direction is special. Step by step, measurement by measurement, we dismantled the deepest intuition our species has ever had and replaced it with something better. Not a comfortable illusion, but a true description of how the universe actually works. That is extraordinary. Other species on Earth have evolved their own remarkable relationships with direction. Migratory birds navigate using magnetic fields. Bees orient by the polarization of sunlight. Fish use currents and salinity gradients. Each of these is a beautiful adaptation to the local conditions of one planet. But none of these species questions its sense of direction. None of them wonders whether down might be local rather than universal. None of them builds a satellite to test whether the universe has a preferred axis. Only we do that. Only humans look at the most reliable signal their body has ever received and say, but is it really true at every scale? Let me check. And the answer, when we check, turns out to be no. The direction we trust most is not universal. The feeling we rely on most is not cosmic. And learning this does not diminish us, it elevates us, because we are the only beings we know of, anywhere in the universe, who have figured this out. Every civilization that ever developed spaceflight on any world, around any star, in any galaxy, will eventually confront this same disorientation. they will leave their home world and discover that the down they trusted is local. They will look for up at larger and larger scales and find only competing reference frames. They will analyze their version of the cosmic microwave background and find perfect isotropy, and they will arrive at the same conclusion we have. The universe has no top, the universe has no bottom. The universe is open in every direction, equally, forever. We got there first, as far as we know. On this small world, orbiting this ordinary star in this one spiral galaxy among trillions, a species that evolved to feel down in its bones looked up and realized that up is an invention. Not a bad invention, not a useless one, but an invention all the same, local, contingent, human. So the next time you stand outside on a clear night and look up at the stars, remember what up actually means. It means away from the center of the Earth. That's all. It's the direction opposite to the pull of gravity at your location. It's real, it's useful, and it keeps you alive every day. But it's not cosmic. It's not universal. It's not absolute. Someone standing on the opposite side of the planet is looking up in the opposite direction, and they're just as correct as you are. And if you could somehow fly above the solar system, above the ecliptic, above the sun's poles, above the Milky Way's disk, you would not be getting closer to some cosmic up. You would just be moving away from specific local structures. The space above the Milky Way's disk is no more up than the space below it. The space above the ecliptic is no more up than the space beside it. These are all just regions of the same vast, directionless, isotropic universe. The title asked why it's impossible to go up in the solar system. And now you know the answer. It's not that something stops you, it's that there's nothing to go toward. Up is not a place. It's not a direction written into the fabric of the cosmos. It's a feeling generated by gravity, a label applied by convention, a useful fiction that works perfectly on the surface of a planet and dissolves the moment you leave. The universe has no top. It has no bottom. It has no ceiling and no floor. It has only space, stretching equally in every direction, and within that space, mass and motion and light and time, all operating under laws that treat every direction with perfect, beautiful, impartial equality. You can go anywhere. You can point yourself in any direction. You can travel above every planet, every star, every galaxy, but you cannot go up. Because in the deepest, truest sense of the word, there is no up to go to. There never was. And the fact that we can understand this, that creatures evolved on the surface of one small world, can look out at the cosmos and recognize that the direction they've trusted their entire lives is not universal. That is one of the most remarkable achievements of the human mind. We overcame our own wiring. We looked past the illusion that evolution burned into us and saw the universe as it actually is. Symmetrical, directionless, and endlessly, beautifully open. Thank you for taking this journey with me tonight. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps this channel keep exploring the cosmos, one deep question at a time. And the next time someone asks you which way is up, you'll know the real answer. It depends on where you're standing, what you choose as your reference, and what question you're really asking. Because in the universe, every direction is equal, and that might just be the most profound thing about it. Good night. And the next time you look up, appreciate the view, knowing that your up is yours alone, shared by no one else in the cosmos who isn't standing right beside you.